Hello, I'm Martin Wimpress, Senior Director of Developer Relations and Community at Slim.AI. Today I'll be sharing 5 practical examples of best practices you can start using right now to better secure your production-ready containers. First, I'll briefly introduce Slim.AI. Slim.AI was created to give developers the power to build safer cloud-native applications with less friction. In connection with our open source DockerSlim, the Slim SaaS platform allows developers to optimize their containers, reducing both overall size and vulnerability count. By increasing efficiency and decreasing the attack surface, Slim.AI ensures that you're only shipping what you need to production. Today, I'm going to present 5 security best practices for your production-ready containers. I'll briefly introduce our sample application for the day. Then I'll look at container best practice using several techniques with a focus on where it impacts security. You should understand exactly what you're shipping to production. I'll introduce several tools you can start using to help with that. We'll make an objective decision about the best base image for our example application, and finally we'll minify the container image with DockerSlim to significantly reduce the attack surface. Now, for those of you that are too long didn't watch, I'll be using techniques and tools today, and this is what you can expect to achieve. So we can go from an application container image of 937 megabytes with over 1,000 vulnerabilities to one that is 25 megabytes in size with 0 vulnerabilities. All images I'll show in this presentation are uncompressed sizes. So let's take a look at our example app. We're going to use a Python example. It's a very simple Python Flask app that implements an even simpler RESTful API. This app is just for illustrative purposes. Its function is unimportant. We could have used Node or any number of other languages. We'll containerize this app using 4 base images and differing container image composition techniques. So let's take a look at just one of the Docker files to get us started. This Docker file adheres to container best practice. It uses the official Python base image. A work directory is defined for our app. It has good layer construction to minimize cache invalidation and optimize build performance. Files are copied only as required, a port is exposed, and it uses an entry point for proper signal handling. But there are a few more things here that specifically help with container security, so let's take a look at some of those. If you do not specify a user in your Docker file, your app will run as root. Nobody is an unprivileged system account. It is available by default in Debian, Ubuntu, Alpine, Distroless, etc. The Nobody account is intended to run things that don't need any special permissions. It's usually reserved for services so that if they get compromised, the would-be attacker has minimal access and impact to the rest of the system. By contrast, if your app is running as root and the would-be attacker potentially has complete access to the container, and then possibly has access to tools and utilities shipped inside the container that they can now use to disrupt your operations and infrastructure. Choosing a version number for your base image is often referred to as pinning. Some tutorials teach newcomers to pin their images to the latest tag. However, containers were meant to be ephemeral, meaning that they can be created, destroyed, started, stopped, and reproduced with ease and reliability. Using the latest tag means that there isn't a single source of truth for your container's bill of materials, resulting in your container getting whatever the most recently updated version is. A new revision to the latest tag can introduce major version bumps of the system and the language that you're using, which will likely introduce breaking changes. Pinning a specific major and minor version in your Docker file is a trade-off. You're choosing to not automatically receive system upgrades and language improvements and fixes via updates, but most DevSecOps teams prefer to employ security scanning as a way to control updates rather than dealing with the unpredictability that comes with container build and runtime failures. We'll now see how specifying the base image tag can be helpful. Avoiding run apt-get upgrade in Dockerfile was considered best practice. In the majority of cases, this is not good advice. Base images from vendors and large projects are frequently updated using the same tag to include critical bug fixes and security updates. However, there can often be delays between the updates being published in the package repositories and the revised base images being pushed to the registries. Relying on the base image alone is not sufficient, even from images blessed by Docker and maintained by companies with plenty of resources. Now imagine a small open source project maintained in somebody else's time. That delta can be significantly bigger. If you pin a stable base image, package updates are purely focused on security fixes and severe bug fixes. You can safely apply system updates without fear of unexpected upgrades that may introduce breaking changes. But you do need to be sure you really are applying the latest updates. Docker builds can be slow, so we use layer caching to reuse build steps from prior builds to speed up the current one. While this does improve build performance, there's a potential downside. Caching can lead to insecure images. For most Dockerfile commands, if the text of the command hasn't changed, the previously cached layer will be reused in the current build. When you're relying on caching, those apt-get, install, update, upgrade, run commands will add old, possibly insecure packages to your images, even after your distro vendor has released security updates. Sometimes you're going to want to bypass the caching. You can do this by passing two options to Docker build, --pull, which pulls the latest version of the base Docker image instead of using the locally cached one, and --no cache, which ensures all the additional layers in the Docker file get rebuilt from scratch instead of relying on the layer cache. If you add those two arguments to a Docker build, the new image will have the latest system level packages and security updates. If you want both the benefits of caching and to get security updates within a reasonable amount of time, you'll need two build processes. A normal image build process that happens whenever new code is released, and every night rebuild your container images from scratch using docker --pull --no cache to ensure you have the latest security updates. Now we have a container image that adheres to best practice. What's actually inside it? I'm not going to deep dive into container vulnerability scanning or generating software bill of materials, also known as SBOMs. That could well be a talk in its own right. However, you should absolutely perform vulnerability scans and generate SBOMs in your production container image build pipelines and review the results. These are also extremely useful tools in understanding what's in your container and what you are shipping to production and what your potential exposure is. Docker has integrated vulnerability and SBOM scanners with Docker Scan powered by Sneak and Docker SBOM, which is powered by Sift. For the purposes of this presentation, I've used the Slim.AI SaaS, which has Grape integrated. Other scanners are available from Sneak, Trivy and Claire, and I recommend you give them all a try. The Slim SaaS can also support other scanner integrations as well. I also used the Slim SaaS, and more recently I used the Slim Docker extension to demystify containers and really get to know what's inside them. Knowing what's in a container is critical to securing your software supply chain. The Slim SaaS platform lifts the veil on container internals so you can analyze, optimize, and compare changes before deploying your cloud-native apps. Let's use container scanning and analysis to determine what's the best base image for our example application. The regular official Python latest base image is built from Debian 11 and weighs in at 921 megabytes, but smaller starting points are available. I'll containerize our example app using 4 different base images, including the official Python image based on Alpine 3.16, the official Python image using their Slim version based on Debian 11, a distroless multi-stage build, and an Ubuntu 22.04 base image, which doesn't include Python by default, so that will have to be installed via a Docker run command. Which leads us on to the next topic, which is installing fewer packages. Sometimes it is necessary to install additional system packages as dependencies of your application or to otherwise help build your image. The Ubuntu base image doesn't include Python, so that needs to be installed using apt-get via the Dockerfile run command. The default options for system package installations with Debian, Ubuntu, Red Hat Enterprise Linux can result in much bigger images than you actually need. That 921 megabyte Python latest base image I mentioned earlier is a good example of package excess. More packages make the container image larger, which in turn increases the attack surface of your container. So when you need to install system packages, avoid installing the recommended dependencies. I've included examples here for Ubuntu and RHEL that install Python 3 without the unnecessary recommended packages. Using --no install recommends in my Ubuntu based image reduces the container size by 300 megabytes. So let's build our app with each of these base images and see how the final image sizes stack up against one another. Here are the results in terms of image size. The images all include Python, our example app and its dependencies, which comprise of 11 packages that are installed via pip. The adage goes that smaller is safer. A smaller image size should correspond to fewer packages, and that should result in fewer vulnerabilities. So let's check that. There's no denying that the Alpine results here are excellent. There are 0 vulnerabilities. The official Python image is based on Debian 11 and it's not looking so great, however, with 86 vulnerabilities, of which 3 are critical and 13 are high. These are all in system packages installed via apt. Distroless, also based on Debian 11 for this particular build, has 50 vulnerabilities, and of those 3 are critical and 7 are high. Again, these are all system packages installed via apt or provided by the apt packaging system. And with distroless, it's also difficult to do much about that because unlike traditional Debian-derived images, there is no apt-get in the container to install the latest packages. This can be worked around, but it's non-trivial. And that brings us to Ubuntu. Of equal size to the Python image, but has the second best vulnerability assessment with no critical or high vulnerabilities at all. Just 3 medium and 13 low-risk vulnerabilities and 8 negligible. So why is this? Ubuntu is derived from Debian, right? Well, Ubuntu is a commercially backed Linux distro with a full-time security kit team that has SLAs to mitigate vulnerabilities for their customers, which includes mitigating all critical and high vulnerabilities for the supported lifetime of the distro. Debian is a community project, and while many Debian contributors, including myself, do fix security issues in Debian, it simply cannot provide the level of commitment to security that a commercially backed Linux distro, such as those from Canonical, Red Hat and SUSE do. The Python image based on Debian 11 is the same size as the Ubuntu-based image, but has nearly 4 times the number of vulnerabilities. It's also worth noting that the high-risk vulnerability CVE 2021-3999 that exists in glibc remains in the images based on Debian 11, such as distroless and that official Python image. unlike Ubuntu, where it has already been mitigated, and Alpine, where it never existed by virtue of Alpine using Muscle. In fact, CVE 2021-3999 is marked as a won't fix, along with 6 medium, 6 high, and 3 critical vulnerabilities identified in my distroless container image. These are known vulnerabilities that the Debian project will not fix in Debian 11 and will therefore not be fixed in any distroless or any other container image based on Debian 11. So, Alpine is the clear winner here, right? Sadly not. Python, Node and some other languages can result in significantly slower build times and introduce runtime bugs and unexpected behaviour. This is due to the differences in Muscle used in Alpine as opposed to glibc used in most other distros. This topic could also be a talk in its own right. Personally, I don't recommend Alpine for Python apps, but it can be great for Go and Rust. But what if? What if I could have the low complexity of maintaining Ubuntu-based container images and the security profile of Alpine? What if I can make container images smaller than Alpine? Well, let's try that. The terms slim, minify and optimize are used interchangeably to describe the act of reducing the size of a container image. DockerSlim is a free open source software that's available on GitHub. Both DockerSlim and the Slim.AI SaaS platform can automatically optimize your containers. Don't change anything in your container image and minify it by up to 30 times, making it more secure and reducing the attack surface of the container. DockerSlim has been used with Node.js, Python, Ruby, Java, Golang, Rust, Elixir, R, PHP, running on Ubuntu, Debian, RHEL, CentOS, Alpine and distroless and many others. But we always get asked how DockerSlim works. So here we go. DockerSlim optimizes your container images by understanding your application and what it actually needs using various analysis techniques, including static and dynamic tracing. This means things like ptrace and analyzing LDD output. DockerSlim will throw away what the container doesn't need. It will generate a new single-layer container image that is composed from only those files in the original unoptimized image that are actually required for your app to function. You can understand the container image before and after optimizing it using either the Slim SaaS platform or the Slim.AI Docker extension, and that will show you exactly how your container image was changed. There are a number of benefits to slimming containers. So, why should you bother? The adage is only ship into production what your app requires, and slim containers can be up to 30 times smaller. Slim container images are faster to deploy due to their lower size, and faster to start due to having fewer files. And slim container images can be less expensive to store and transfer. Slim containers reduce your attack surface. Our report titled What We Discovered Analysing the Top 100 Public Container Images showed an increasing trend of dev, test, QA and infrastructure tooling being left in production-ready containers. Unused shells, interpreters, tools and utilities that are left inside your container images can be used against your infrastructure to disrupt your operations if a container is compromised. So let's take a look at those slimmed containers. In most cases, there are significant size reductions to be had, slimming any container image regardless of build technique or the base image used. In our example here, we can see a 3 to 6 times size reduction. Quite modest, but valuable all the same, as the container attack surface has been significantly reduced. We often see 10 to 30x size reductions for complex applications, and our slim Ubuntu-based image is now just 6 megabytes larger than the optimized Alpine base image. but with none of the compatibility concerns, and it's 35 megabytes smaller than the unoptimized Alpine image. But has slimming also improved the vulnerability assessment? So let's find out. Analysing if vulnerable components exist in slimmed containers is currently a semi-manual task, and we are working on automating this, and you'll see a report of that in just a moment. That said, it only takes a few minutes at most. It really often just takes a few seconds to do most checks, using the Slim SAS or the Slim Docker extension to search for vulnerable components and confirm they're no longer present. We've already confirmed that the Ubuntu base image was free from critical and high-risk vulnerabilities. So that leaves 3 medium-risk vulnerabilities that are in libsqlite 3, Perl base, and zlib. It took a few seconds to confirm that none of those components exist in the Slim image, and using the Slim SAS confirmed that all of the components affected by the remaining low-risk vulnerabilities have also been removed. So yes, we can have our cake and eat it too. We now have an Ubuntu-based image with no known vulnerabilities of comparable size to a slimmed Alpine image with none of the potential complexity of working with Alpine. So what this analysis shows is that Ubuntu is the best base image for our example application. So let's take a look at what we've learned. Following container best practice will set you up for success. Good quality Docker files are the place to start. Always run internet-facing apps and services via unprivileged user accounts. Pin your base images. Use a stable base image and apply updates. Be mindful of layer caching, introducing potentially insecure packages into your container images. Container scanning and analysis are essential to fully understand what's inside your container. Do not install recommended packages to help keep your container slim and secure. Linux vendors have security SLAs, so assess your base image options and pick what is most suitable for your project. You can slim just about any kind of container image, including those based on Alpine and distroless, and slimming removes vulnerabilities and reduces the attack surface. So yes, that was more than 5, and you're welcome. So thanks very much for listening. I hope you've picked up a few tips to help improve the security of your containers. We invite you to give the Slim SAS or the Slim Docker desktop extension a try. Both are free to use. Also take a look at DockerSlim and take it for a spin. If you have any follow-up questions, join the Slim.AI Discord. The QR code is available there. And ask. We're happy to help. Or you can follow us at SlimDevOps on Twitter and ask us there. Keep building.
Thanks for the great talk. As I said, we do have a speaker gift. It's in the post. I'll be honest, I don't know if it's in the post. That's somebody else's issue to deal with. But thanks again for the time. We have arrived to the final Q&A of the day. We do have one question. Tricky one. So the slimming of the image sounds awesome, and it does actually sound awesome. Are there any caveats, downsides to it?
Yes. As with all things, there's always some caveats, but they're trivial to work with. So the issue that we see most often with sort of more complex applications, even if it's a microservice with a complex REST hierarchy, for example, or maybe an app that has some static assets, is if while DockerSlim is observing the application in order to determine what it should keep, to put inside the minified container, if any assets are not touched in any way, read or loaded, then they will be absent from the minified container. So there are a couple of mechanisms that are provided by DockerSlim to counter that. you can provide it with a set of URLs specifically to crawl if you know that there are particular URLs that may not be hit. The best thing to do is during that observation stage, if you've got integration tests, is run those integration tests. So produce your container image in the usual way and then have an additional step in your CI/CD that runs the minification process exercising the same integration tests. That should give you enough execution path coverage that the minified container has everything inside it. But we made like an image carousel demo recently for an educational thing we were doing on our own live stream, and we found that some of the static images in the carousel were absent. So another thing you can do is if you know there are paths in your application with static assets that you always want to include in the minified container, there are flags to say always include these paths. And you can, manipulate the way the crawler works in different ways as well. You can even completely disable the HTTP probe process, and you can just use DockerSlim to minify command line applications. Okay. So we did a workshop on the Raw Code Academy last week. So if you're familiar with their YouTube channel, we went through all of the sort of potential bear traps and the trivial ways that you can work around those during that presentation.
Cool. A few other questions came up. Is the Slim extension just for Docker Desktop or also Docker CLI?
The Slim extension is a Docker Desktop extension. So that's in the Docker extension marketplace. We were a Docker Desktop extension launch partner. In terms of command line usage, DockerSlim is available from GitHub. It's a Go binary. You just integrate it into your tooling, and it then calls on Docker in order to do all of the observation and minification for you.
Okay. Got two more questions. Can the slimming also run with Podman other than non-Docker container runtimes?
At the moment, the only runtime that we support other than Docker, and it is experimental, it's coming very soon, and that's running in a Kubernetes cluster. And we gave that demonstration by building DockerSlim from source on the Raw Code Academy a few days ago, but Podman and ContainerDays is coming soon, TM.
Cool, awesome. And finally, how do you deal with the need to debug a running container, requiring some tools like a shell?
Yeah, indeed. So we have a mechanism whereby you can attach a debug instrumented sidecar container to the slimmed container, and we have a number of documents and blog posts on our website that go through that. But if you want to get into that and you're struggling to get started, just come and ask. We'll be happy to point you in the right direction.
Yeah, so similar to the recent ephemeral pods on Kubernetes, I'm assuming, where you can attach something and use the shell as a one-time thing. Cool, awesome. Thanks, Martin. Again, that's it for today. We've struggled along, we've managed, we've had a few hiccups. Thanks again, Martin.
You're welcome. Thank you for having me.